and I'm from Hong Kong, and I would like to share with you on my state-of-art review on Outrigger system. You'll probably, in terms of content, basically we'll talk about a couple of areas, which is examples, and also with some other issue in Outrigger design. Adjustable outrigger lateral casting, damper outriggers, and also what we call a shear fuse hybrid system. And also at the end is a summary. In my visit in Sydney and Melbourne, especially yesterday, I visited one of the tallest buildings in Melbourne, and also used the outrigger system. And also in the previous section, the speaker also mentioned outrigger system. So outrigger system is not new to this region, right, or Australia. And also it has been applied for a number of projects over the world. In case you didn't know, I mean, outrigger is something which is to enhance the structural lateral stiffness. If I take my body as a core, right, if you push it and to resist this lateral will adjust my body. If I can stretch my arm on the other side and mobilize, say, if I have two column, right, then I mean the lateral system is, I mean the lever arm is much larger, and so the resistance is much stronger, right? Just like, you know, you go for ice skating and so forth, and this is what we call, sometimes we still have this outrigger action, right? For outrigger, I mean, this is this is what it means in case of the a core. Right, you go to a lateral load, apply to it, and this is the moment. And you got a moment and shear force, and also we have a tension and compression. And in the case we have a very stiff arm, you will increase the stiffness of these two beams, let's say, and you will see that, you know, we'll get an increase in the tension force and compression force, and also the moment will in the core will release. So that for this system, we can mobilize the perimeter structure, and also at the same time reduce the force in the moment in the core, and so that you can reduce the core and also to control, increase the stiffness. So in terms of the force and moment, you can look at from this simple diagram. I mean, this is the moment curve for the for this system, original one. If you don't have an outrigger, right, just pure cantilever. And if you have a cantilever, basically you actually have reduced the moment actually by using this coupling this perimeter structure. So the moment in the core will reduce. And also actually this line is a parallel line, right? You can't make it unparalleled, it will parallel. And also you have like a M1 and M2, right? And this is the simple equation. Basically, this shows that why the moment the base of the core is reduced by this amount of M1 plus M2. So you can consider in the case whether you want you will have a lot of this outrigger system along a tall building, and you will have M1, M2, M3, M4, M5. So the total base moment will supposed to be reduced, but you cannot be ideally down to zero, definitely. But also we need to think about, you know, for system, whether we should have a 2 outrigger, 3 outrigger, what is the stiffness of outrigger, etc. Which is the stronger the outrigger, the larger the M1 or the M2, right? So it means the amount of this reduction will be more. But you're putting more money on the outrigger, you should or have a thicker core. It is always a optimization study, right? And also it depends on the requirement, etc. Right? Sometimes you want to have, if you want to have you will say you go for mega column, right? That means that you got a stronger column, and you want to reduce the core, right? You will say, I wanted the perimeter structure, yeah, I want to control the stiffness, but the perimeter structure, I still wanted to keep a minimum. That means that you can also adjust so that, you know, not to be very, very steep outrigger, and then you get a thicker core. But the perimeter structure is getting slightly less in dimension. For example, a lot of study in the past, we talk about the location of outrigger, what is the ideal location, right? It'll be probably 1/3, 2/3, or whatever. But in reality, it's not a structural engineer choice. it's always be a commercial driven. It's always located in the like a refuge floor or mechanical floor, right? So, my previous study research is not on where we put the outrigger, right? Because somebody has done it before, firstly. Secondly, with my experience, it's not a structural engineer choice. So, but my study is on what is the best form of outrigger. This is a control of like the double-story high, 30-meter long span structure from the core to the perimeter, 4.2 meter floor to floor height, right? So it's a double-story high, right? This is typical. Sometimes for some structure, we actually have a triple floor, right? You want to make the it much stronger. For if say you have a one-story high, then the answer may be slightly different, but the outrigger will not be very strong, right? So I make it say for this one is this geometry, this constraint condition. And then I study a couple of 1, 2, 3, 4, and also 5 and 6 and so forth. But what I'm going to show is for this, you look at the paper, basically a study that, you know, for this one is probably in terms of material is the minimum. In terms of stiffness, it's not the strongest, right? But in terms of strength, it's the strongest. It's just because for this one, for this one, C and D, basically this is like a dummy, right? And but for I just want to show it is like a dummy. And C and D, basically all the focus, the failure are only on this member. The utilization on the other member are very low. So basically, although we can have a stiffer structure, right? But in terms of total utilization of material, they are not, right? Unless we adjust the size, right? I'm using a uniform size for this study. So, but sometime, I mean, in the wind control condition, right? I think will be probably most tall building in Australia. What you're looking for is a very stiff outrigger, right? Because you don't have a seismic consideration. But in seismic region, sometimes, you know, we need to be struggle between, you know, whether we should decide for wind or we should use a very steep outrigger or we should use a flexible outrigger, what you call it flexible, or you call it soft sometimes, right? And this is always a choice of engineer and also condition. In terms of rigid outrigger, I mean, this is one of the examples. We have done Hong Kong Exchange Square. It's a concrete structure. And we have a core wall. And also we have a concrete outrigger, right? It's a rigid arm like a wall, right? A one-story wall, right? Complete wall. We will leave the opening for access, right? For this is a mechanical floor, so we need a people to walk across. And this is what I call the rigid outrigger system. And then we have another one, which is a single-story high flexible system, which is used in the China World Trade Center in Beijing. Beijing is an area with high seismicity, right? It's about 0.2 G at 475-year event, seismic event. And for this building, basically, it's 300 meter tall, and basically wind will control a bit, and also seismic will control the bottom. And so what we want to do here is we want to control the interstory drift as a requirement in seismic area, but we don't want to make a very sharp change or sudden change in vertical stiffness, right? And also horizontal stiffness, because outrigger system is a sudden change cause a sudden change in stiffness, which is not ideal in seismic area, right? So what we do is, okay, we make it to be single-story high outrigger system, you know, so that it basically use it to control the wind, interstory drift in what we call the serviceability state, and also for the wind. And for this one, basically you see that is temporarily connected, because when the building goes up, there will be axial shortening. And after that, then we will weld it. I mean, in China, welder is very relatively cheap, I would say. So everything they like to weld rather than bolt it. And this is what we call a flexible system. And also we have other like flexible system by concrete is by Tomasetti in Patron Tower. And basically they cast the beam, all right? And then allow it to construction. And then after the top out, then they cast the column, and so that it increase the stiffness, right? This is one way of doing it, but I would call it still flexible because beam, in terms of the wall, in terms of what I call the rigid stuff, I mean, it's still not very stiff, right? But what they need is probably, again, to control the stiffness. Another one is for all these previous one like this one, they add a column later on and so forth, is because the tower is going to, the perimeter structure and the core will shorten in a different way, right? And what we call the differential shortening. But it's always a debate on whether we should account for all this axial shortening in the design, right? And or we should use it to, or we should see how we could release it. So the way sometimes some for the structure we can account for it, but some of them we decide to release it. For Cheung Kong Center is a 298-meter tall tower in Hong Kong, very strong in wind. We don't consider seismic. The client would like to have very fast construction. Everything is to be composite, and concrete filter tube, 9 days per every 3 floor. This kind of construction speed. And so what we're going to do is to apply what we call a adjustable outrigger. And from this project, we'll learn, we experience, we learn, we understand, will be the floor, the core is using a jump form, which could be we limited to not more than 12 story ahead of the floor. And, but up to the outrigger floor, we find the core is slowed down because we have a lot of welding and embed the steel and so forth and so on. And we are going to tell you how we're going to accommodate in the next project. And for this one, we use an adjustable outrigger. And you will see that, say, for outrigger, when you construct it, and then you have differential shortening, so usually the perimeter will shrink more, right? The perimeter will shrink more, that means that it will be lock-in stresses in the outrigger. And so we are trying to find a way we can release this lock-in force. And also in our calculation, it shows the lock-in forces is equivalent to the same amount of wind force, right? That means that if we're going to take it into account in the design without releasing it, that means we are doubling the force in the outrigger side, in the outrigger. That's why we decide to release it. To release it, we input this like adjustable zone, and which is this is the gap, and the outrigger, and this is the belt truss, or it could be a column, and so we provide a gap, and then we put steel plate during construction, right? Now up to the stage, you say, well, you want, if the designer or the case where you want to connect the core and the perimeter during construction, right? In the probably the first, I can't remember exactly, but about like 30, 40 story, basically we don't need to connect because the core is stiff enough to take all the load. So we don't need to connect it. But up to higher, then we start to use this string pay so that the core and the outrigger start to work, right, for strong wind during construction. And after that, I mean, we have put the strain gauge in the outrigger and so on, measure the strain so that we know the stress and we know the forces being locked in the outrigger. Up to a certain amount, and these forces, we track it and monitor it, and then we, up to the point that we decide we need to release it, and we release the plate. Once we release the plate, the gap will change, right? The gap on the top and the bottom will change. And so that because it's shortened more, and this one is elastic, it will bounce back a little bit, spring back a little bit, right? And so that after that, we have a different size of gap. And with this gap, and then we put another stream pay, and then we continue the process and up to the end of construction, right? This is the construction photo, and we have a belt truss here, and we have the column where the outrigger is not directly hit on the column because the column is relatively small for this project. And we connect to the belt truss and so use the belt truss to move and distribute the force in the perimeter beam. And you will see that this is the connector. And this is the flag jet we use, and also this is the stream pay, right? You will see how we're going to put the steel pay in and so forth and so on. And the beauty of this one is we can use this one to adjust the outrigger during construction up to the end, and also in case the change of use of the building or change in loading in the building later on, we can still adjust it. But of course, I mean, after construction, we will block it, right? We can block it and with fire protection and so forth and so on. But again, this block means by means of other protection, we can remove it, we can still adjust it in the lifetime of the building. Another, as I said, in the Cheung Kong Center, we found that it was slowed down in the core wall and in the outrigger floor. So in the IFC, we have learned the experience, and we still want to try to accelerate the construction progress. And that's why we use a virtual casting technology. And we build the core. Up to the outrigger floor, we build half of the core. And then we continue the core by jump form. And using this, so it got a notch. It got a notch in the core, but the core is still stable, right? The core is still stable. We calculate the thickness requirement and so forth and so on. And after that, we put the outrigger, assemble the outrigger on site, and then we slot in the slot, right? And after that, then we can cast with concrete and so forth and so on, and then we cover up. This is a photo. It shows, you know, the notch of the core, right? And then we put the outrigger inside the core, and then after that, we're going to cover it by concrete. So it still remains as a whole complete core, right? And this is, and also you see the outrigger. So this is the mega column, and you see this is the adjustable outrigger slot, right? So the previous one, adjustable outrigger, still apply to this project. For these two examples I show you is related to construction, and also related to what we call rigid outrigger. This is very stiff outrigger, right? And because we use it to control the wind. But besides this kind of rigid issue, and in the case of where we have a seismic and wind, is again, as I said, I mean, the outrigger, we don't want it to be too stiff. In the wind, we want it to be stiff. So in the case of like a Manila, where we have a very strong wind and very strong seismic, we have another problem. So what to come out is for this St. Francis, we have a twin tower, which two tower is pretty close together. Because the site limited site area, the tower is very close. It caused a lot of issues during wind because of the wind water shedding issue. So to overcome this one, and what we want to make it to be more economic, and so forth and so on, we add additional damping to the building. And how to add additional damping in the building? We need to maintain the stiffness, we need to control the drift, but we want to add a damping. And so we decide to use what we call a damper outrigger. A damper outrigger is a outrigger, and then we put a damper at the top. Because saying these two parts is where you got the displacement, and also you can use it to add additional damping to the system. And so we put the damper there, and at the tip of the outrigger. And this is the 3D model. And you see that a concrete wall, opening for access, and also the outrigger, right? Also the outrigger tip with a damper. The green one is a damper. Well, we design the damper so that you can, it's sufficient, to generate the damping, amount of damping required for this structure. With the additional damping, it controls the vibration of the structure. It reduces the wind load, and also it reduces the seismic load, right? And this is the a photo, site photo. This is what we intend to do. And this is the site photo, and this is the outrigger. We specially design the amount of the damping required. We put the outrigger, and this is the connection, and so forth. And this damper could be replaced, could be inspected, right, and so forth. Again, this damper outrigger, good thing is it generates damping. And the bad thing, not a bad thing, but depends on the stiffness you require. Sometimes because this kind of visco oil damper or viscoelastic damper, it do soften a bit, right? So in a case where we have wind control of the building, but we need to account for 2,500 years earthquake event. What are we going to do? This is always another problem we have for a tower, what we call the Chongqing Waffle City. This is a tower with a project with 6 towers together, and actually each tower has 2 towers or 3 towers. You know, it will come a little bit complicated. And we have a T1, T6, and then we have T1A, T1B, T1C. But I'm not going to talk about the structure, and also because of time, I'm not talking about this conservatory, and we just talk about the system we use for this tall building, which is about 300 meters tall. The building is a bit of curve in this side and straight on the back, and then you have another tower attached to it. The is a 350 meter up to the crown, and we have slender ratio 1 in 9. Very challenging project, and because of the slenderness. Chongqing is not very, do have a wind, but not extremely strong. But we do have earthquake, and also not extremely strong. So we need to maintain the stability of the structure, and is our first target. So basically, the system is a core and mega frame, 4 mega column on the edge, and also we have some intermediate column. Intermediate column, basically, we have released the force, and so that everything will go to, we release the vertical load in every transfer truss, and so that all the load will push to the mega column at the 4 corner to resist the uplift. And then we have what we call the composite outrigger. Chongqing is not what we call the second tier city in China. The economic is not extremely good, but so the client would do not want to use a lot of steel and to reduce the construction cost, so we want to use concrete. So the concrete outrigger, again, the issue is how we're going to control the cracking of the building, of the outrigger, et cetera, et cetera. And so we developed that we want to reduce the construction cost, but we want to protect the building. And so we come up with this hybrid system with a concrete outrigger with the steel tip, with the steel connection, and also we call it steel fuse. And basically, what we do is we special design the tip so that it is elastic during wind, and it will start to yield in 2,500 year earthquake event. And so this you will see that, you know, this one is the formation, and this is the concrete string, and basically control the concrete wall to have an existing cracking. At the same time, for this yield, for this fuse, right, this is like a fuse, actually it start to yield and generate damping and also dissipate the energy in order to protect the building, right? And so this one, we have done a lot of tests with various geometry and so forth and so on. You can see that hysteresis behavior of the fuse is very nice, and we got approval, and also we got a patent in China. So in summary, basically I have covered the various kind of outrigger in terms of design and also in terms of construction. And also we have present the damper outrigger, also a hybrid outrigger with a shear fuse. And all these have been keep track, and also I've been working in the Council of Tall Building Urban Habitat outrigger working group, and we have produced document for that. And the first edition of the outrigger design for high-rise building was published in 2012, and I was told will probably around 5,000 copies, and then it was sold out in about 2015. And so we are going to this in the past, and we have been discussed whether we should reprint it, get a reprint of it, or we should update it. So we decided to update it, and so all the one I mentioned to you previously have been incorporated in the second edition, which was just been announced and been book launched on Monday in Sydney during the conference, right? So if you have you want to know more about the outrigger design and so forth, you can refer this code practice. Basically, this book, and basically the major changes is on the chapter 3 and 4, And this is the Outrigger members of the Outrigger working group for this booklet. Okay, thank you.